There's a star out there that shouldn't exist. It's called SDSS 008-0939, and according to everything we understand about stellar evolution, it died billions of years ago. Yet there it sits in our telescopes, burning bright, mocking our physics. This isn't science fiction. This is the universe reminding us that we're children playing with toys we don't fully understand. You look up at the night sky and see points of light. Peaceful, eternal, stable. You couldn't be more wrong. Every single star you're looking at is a catastrophe in slow motion, a barely controlled thermonuclear explosion held together by nothing more than its own gravity. The only difference between a star and a bomb is time. Stars just take longer to detonate. Let's talk about what stars really are, because the story you were told in school barely scratches the surface. You learned that stars are giant balls of gas fusing hydrogen into helium. That's like saying the ocean is wet. Technically true, but you're missing the violence, the complexity, the sheer impossibility of what's actually happening. Inside the core of a star like our Sun, the temperature reaches 15 million degrees Celsius. At these temperatures, matter doesn't behave like anything you've ever experienced. Atoms are stripped down to their nuclei. Electrons are torn away and exist as a separate plasma sea. The pressure at the core is 250 billion times Earth's atmospheric pressure. If you could somehow survive the heat, the pressure alone would crush you into a space smaller than an atom. And in this hellscape, hydrogen nuclei are moving so fast, colliding so violently, that they overcome the electromagnetic force that should keep them apart. When two protons fuse, they don't just combine, they transform. One proton converts into a neutron through weak force interaction, releasing a positron and a neutrino. This is quantum mechanics and nuclear physics having a conversation at energies that would make particle accelerators jealous. Every second, the Sun converts 600 million tons of hydrogen into helium. 600 million tons every second. It's been doing this for 4.5 billion years, and it has enough fuel to continue for another 5 billion years. The energy released from this fusion is so immense that a single second of the Sun's output could power human civilization at current consumption rates for 500,000 years. But here's what keeps physicists awake at night. The photons created in the Sun's core don't immediately reach us. A photon born in the centre of the Sun begins a journey that should take about 2 seconds, if it could travel in a straight line at light speed. Instead, it takes somewhere between 100,000 and 1 million years to reach the surface. Why? Because the Sun is so dense, so packed with matter, that photons are constantly absorbed and re-emitted by atoms. They random walk through the solar interior, taking a drunkard's path that extends their journey by a factor of billions. Think about that. The sunlight touching your face right now was created before humans existed. Those photons began their journey when our ancestors were still figuring out how to make stone tools. By the time they finally escaped the Sun's surface and travelled 8 minutes to reach Earth, entire civilizations had risen and fallen. Now let's scale up. Our Sun is a G-type main sequence star. It's medium-sized, middle-aged, completely average. The universe doesn't care about average. Out there in the cosmos are stars that make our Sun look like a candle next to a forest fire. UY Scuti is one of the largest known stars. If you placed it at the centre of our solar system, its surface would extend beyond the orbit of Jupiter. The volume of UY Scuti is approximately 5 billion times that of our Sun. 5 billion. You could fit our entire solar system inside this star with room to spare. And yet, despite its immense size, UY Scuti contains only about 30 times the Sun's mass. It's so diffuse, so spread out, that its outer layers are nearly a vacuum by Earth standards. But size isn't everything. R136 SA1, located in the Tarantula Nebula, is the most massive star we've ever found. It contains 315 times the mass of our Sun. The surface temperature exceeds 50,000 Kelvin. It's so hot that it appears blue, and the radiation pressure from its light is strong enough to blow away its own outer layers. This star is losing mass through stellar wind at a rate that would consume Earth's entire mass in about 800 years. The luminosity of R136a1 is 8.7 million times that of our Sun. If you replaced our Sun with R136a1, Earth wouldn't just be vaporized. The sheer radiation pressure would blow our planet apart like dust before the solar wind even had a chance to incinerate us. We would simply cease to exist as a coherent object. These massive stars live fast and die young. While our Sun will burn for 10 billion years, a star like R136a1 will exhaust its nuclear fuel in just a few million years. It's the ultimate cosmic trade-off. The more massive you are, the hotter you burn, and the faster you consume yourself. And when these giants die, they don't fade quietly. They explode. Supernovae are not just explosions. They're the universe's way of recycling matter, of creating elements, of seeding galaxies with the building blocks of planets and life. Every atom in your body heavier than hydrogen was forged in the core of a star or in the catastrophic violence of a supernova explosion. You're literally made of stardust, but not the gentle poetic kind. You're made of the shrapnel from stellar detonations. There are two main types of supernovae, and they're fundamentally different processes. Type Ia supernovae occur in binary star systems, where a white dwarf accumulates matter from a companion star. When the white dwarf's mass exceeds the Chandrasekhar limit of approximately 1.4 solar masses, electron degeneracy pressure can no longer support it. The star collapses and rebounds in a thermonuclear explosion so powerful that it briefly outshines its entire host galaxy. Type II supernovae are core collapse events. They happen when massive stars, at least 8 times the Sun's mass, run out of fuel. For millions of years, these stars have been fusing elements in their cores: hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to silicon. Each fusion stage releases energy that supports the star against gravitational collapse. But there's a wall, a hard stop that physics won't let you pass: iron. When you fuse elements lighter than iron, you release energy. When you try to fuse iron, you consume energy. Iron is the cosmic dead end. Once a massive star's core is converted to iron, fusion stops, and without fusion, there's no radiation pressure to hold the star up. What happens next occurs faster than you can blink. The iron core, roughly the size of Earth but containing 1.5 times the mass of our Sun, collapses. In less than a second, it shrinks from thousands of kilometers in diameter to about 20 kilometers. The collapse happens so fast that the infalling matter reaches speeds of 70,000 kilometers per second, 23% the speed of light. The density becomes so extreme that protons and electrons are forced together, combining into neutrons and releasing neutrinos. So many neutrinos that for a brief moment the core outshines the entire electromagnetic output of the universe in neutrino radiation. These ghost particles, which normally pass through matter as if it weren't there, become so numerous and so energetic that they carry away 99% of the supernova's energy. The core collapse triggers a rebound. A shockwave tears back through the star's outer layers at speeds exceeding 30,000 kilometers per second. The star explodes. In a matter of hours, a single star releases more energy than our Sun will produce in its entire 10 billion year lifetime. For a few weeks, one dying star can outshine an entire galaxy of 200 billion stars. The explosion is so violent that it creates elements that cannot be formed any other way. Gold, platinum, uranium, all the heavy elements that exist in nature are forged in the brief seconds of a supernova explosion. The gold in your wedding ring, the uranium powering nuclear reactors, the platinum in catalytic converters, all of it was created in stellar death throes. And sometimes, the core that remains is even stranger than the explosion itself. Neutron stars are objects that shouldn't be possible. They're the crushed cores of massive stars, the remnants left behind after supernova. Imagine taking 1.5 times the mass of our Sun and compressing it into a sphere 20 kilometers across. A neutron star is so dense that a teaspoon of its material would weigh about 4 billion tons, more than all the cars, buildings, and people on Earth combined. The physics at work inside a neutron star is extreme beyond comprehension. The gravity is so strong that if you somehow stood on the surface, you would weigh about 200 billion times what you weigh on Earth. Your body would be instantly crushed into a layer of atoms roughly 1 atom thick. Mountains on neutron stars, if they exist at all, are less than a millimetre tall. The gravity simply won't allow anything higher. The interior of a neutron star is one of the most exotic places in the universe. The outer crust is made of atomic nuclei crushed into a crystalline lattice, with electrons flowing between them. As you go deeper, the nuclei merge into increasingly bizarre shapes. Nuclear physicists call them nuclear pasta, layers of matter arranged in gnocchi, spaghetti, and lasagna configurations based on their structure. These aren't cute names, they're descriptions of how protons and neutrons organise under pressures that don't exist anywhere else in the universe. Go deeper still, and you reach the outer core, where matter exists as a neutron superfluid. Individual neutrons flow without friction, creating vortices and quantum effects on macroscopic scales. The inner core is even more mysterious. We simply don't know what happens to matter at those densities. It might be a quark-gluon plasma, a strange matter core, or something we haven't even theorized yet. Neutron stars rotate, some of them rotate very, very fast. The fastest known pulsar, PSR J1748 2446 AD, spins 716 times per second. 716 rotations every single second. The surface of this neutron star is moving at approximately 24% the speed of light. At these speeds, the star is nearly spherical despite its rotation, held in shape by gravitational forces strong enough to overcome the centrifugal force trying to tear it apart. These rapidly rotating neutron stars often have intense magnetic fields, billions of times stronger than any magnet we can create on Earth. Some neutron stars, called magnetars, have fields so powerful that they warp the quantum vacuum itself. A magnetar's magnetic field, at a distance of 1,000 kilometers, is strong enough to fatally disrupt the molecular bonds in your body. You would simply come apart at the atomic level. In 2004, a magnetar designated SGR 1806-20 experienced a starquake. The crust of the neutron star fractured and reset, releasing a blast of gamma rays and X-rays that reached Earth from 50,000 light-years away. In 1/10 of a second, this explosion released more energy than our Sun produces in 150,000 years. The radiation was so intense that it measurably affected Earth's ionosphere, disrupting radio communications from 50,000 light-years away. If that starquake had occurred within 10 light-years of Earth, that is, radiation would have stripped away our ozone layer and likely caused a mass extinction event. We were safe only because of distance. The universe is terrifyingly large, and that size is sometimes the only thing protecting us from its violence. But neutron stars aren't the final form. When a star is massive enough, even neutron degeneracy pressure cannot halt the collapse. The core continues to compress. At some critical density, something breaks. The laws of physics as we understand them reach a boundary, and what emerges on the other side is perhaps the most disturbing object in the universe, a black hole. Black holes are not holes, they're not empty space, they're objects, incredibly dense objects, with mass, with gravity, with measurable physical properties. But calling them objects doesn't quite capture what they are. Black holes are places where the geometry of space-time itself has been damaged, where the fabric of reality has been pushed past its breaking point and torn. Let's start with the simplest black hole, a non-rotating, electrically neutral black hole called a Schwarzschild black hole. It's defined by a single property, mass. Everything else about the original star, its composition, its structure, its history is gone, erased. There's a theorem in physics called the no-hair theorem, which states that black holes have no distinguishing features beyond mass, charge, and angular momentum. Everything else is hair, irrelevant details that get erased during collapse. The defining feature of a black hole is the event horizon. This is not a physical surface. There's nothing there you could touch. It's a boundary in space-time, a point of no return. Once you cross the event horizon, every direction you can travel points toward the center. Up is toward the singularity, down is toward the singularity, left, right, forward, backward, all lead to the singularity. Your future is constrained to a single point, and there is no physical process that can prevent you from reaching it. The size of a black hole's event horizon depends on its mass. For a black hole with the mass of our Sun, the Schwarzschild radius, the distance from the center to the event horizon, is about 3 kilometers. For a black hole containing 10 solar masses, the radius is 30 kilometers. The relationship is linear. Double the mass, double the radius. This creates a profound implication. The density required to form a black hole decreases as mass increases. A stellar mass black hole of 10 solar masses has an average density higher than an atomic nucleus. But a supermassive black hole of 4 billion solar masses, like the one at the center of our galaxy, has an average density less than water. If you could somehow scoop out a sphere of space with the same radius as this black hole's event horizon, fill it with water, it would collapse into a black hole. The universe's most extreme objects can form from densities you encounter every day as long as there's enough mass collected in one place. What happens if you fall into a black hole? The answer depends on who's watching. From an outside observer's perspective, you never actually cross the event horizon. As you approach, your image appears to slow down, redshift, and freeze just above the boundary, asymptotically approaching but never quite reaching the horizon. You fade from view as the light from your body stretches to longer and longer wavelengths, eventually disappearing into the infrared and radio spectrum. From the universe's perspective, you're stuck at the event horizon forever. But from your perspective, something very different happens. You cross the event horizon in finite time. There's no barrier, no wall, no indication that you've passed the point of no return. If the black hole is large enough, you might not even notice anything unusual at first. The tidal forces, the difference in gravitational pull between your head and your feet might be quite gentle for a supermassive black hole, but they won't stay gentle. As you fall deeper, the tidal forces increase. Your body begins to stretch. This process has a technical name, spaghettification. The gravity gradient becomes so steep that different parts of your body experience vastly different accelerations. Your feet, closer to the singularity, are pulled harder than your head. The difference becomes larger than molecular bonds can withstand. You don't just die. You're pulled apart at the atomic level, transformed into a stream of particles falling toward the center, and at the center, at the singularity, something waits that we cannot describe. Our physics breaks down completely. General relativity predicts infinite density, infinite curvature of space-time. These infinities are a sign that the theory is incomplete, that we're missing something fundamental about how reality works at these extremes. Most black holes aren't simple Schwarzschild solutions. They rotate. When a massive star collapses, it conserves angular momentum. The rotation speeds up just like an ice skater pulling in their arms. The result is a Kerr black hole, and it's even stranger than a non-rotating one. A rotating black hole drags space-time around with it. This effect, called frame dragging, means that space itself is moving. If you tried to remain stationary relative to distant stars near a rotating black hole, you would find it impossible. The space-time you're embedded in is being swept along like a current. Within a region called the ergosphere, outside the event horizon itself, you cannot remain still. You must rotate with the black hole. The interior geometry of a rotating black hole includes features that sound like science fiction. The singularity is not a point but a ring. Under the equations of general relativity, this ring singularity might be traversable, leading to other universes or other regions of space-time. There are solutions that include closed time-like curves, paths, through space-time that loop back on themselves, allowing travel to your own past. Do these features exist in reality? We don't know. The interior of a black hole is forever hidden from outside observation, and the theoretical pathways through ring singularities require conditions that probably cannot exist in our universe. They're mathematical possibilities that physical reality likely forbids. But the fact that they appear in our best theory of gravity tells us something important. Our understanding of space-time is incomplete. Black holes aren't invisible. They affect everything around them. Matter falling into a black hole doesn't drop straight in. It forms an accretion disk, a swirling maelstrom of superheated gas orbiting at relativistic speeds. The friction in this disk heats matter to millions of degrees, hot enough to emit X-rays. Some of the brightest X-ray sources in the sky are black holes feeding on nearby stars. The energy released by matter falling into a black hole is staggering. Through a process called the Penrose mechanism, or through magnetic field interactions in the accretion disk, black holes can convert mass to energy with an efficiency of up to 42%. Nuclear fusion, by comparison, converts about 0.7% of mass to energy. Black holes are the most efficient engines in the universe. Some black holes produce jets, narrow beams of particles and radiation shooting out from the poles at nearly the speed of light. These jets can extend for hundreds of thousands of light years, pumping energy into intergalactic space. The mechanism involves the black hole's rotation and magnetic fields threading through the accretion disk. The details are complex, still not fully understood, but the result is undeniable. Black holes, objects from which light cannot escape, can be among the brightest objects in the universe. At the centres of most large galaxies, there are supermassive black holes. Our own Milky Way hosts Sagittarius, A star, a black hole containing approximately 4 million solar masses. It sits quietly at the galactic centre, occasionally flaring as small amounts of matter fall in. But it's gentle compared to active galactic nuclei, black holes that are actively feeding. The Quasar 3C273 is powered by a black hole containing roughly 880 million solar masses. It's so luminous that it outshines the entire galaxy surrounding it. The total power output is approximately 4 trillion times the luminosity of our Sun. And this is just from matter falling into a region the size of our solar system. The efficiency is breathtaking and terrifying. We've recently begun to observe black holes directly. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the dark region created by the event horizon against the backdrop of the glowing accretion disk. The black hole, designated M87 star, contains 6.5 billion solar masses. The image shows a ring of light, photons bent and focused by the black hole's gravity, surrounding a dark centre. This wasn't easy. The black hole is 55 million light-years away. Photographing it required creating a virtual telescope the size of Earth, synchronizing observations from multiple radio telescopes across the globe. The data processing alone took years, but the result was worth it. For the first time, we saw direct evidence of the event horizon, confirming predictions made a century ago by Einstein's theory of general relativity. In 2022, they released an image of our own galactic centre black hole, Sagittarius A star. Smaller and closer, but more challenging to image because the accretion material orbits so quickly. The images match theoretical predictions with eerie precision. The universe follows the math, even at extremes where our intuition completely fails. Black holes represent the ultimate cosmic compression. But stars can exist, in other extreme states, balanced on the edge of collapse without quite falling over. These are the degenerate stars, objects supported not by thermal pressure from fusion, but by quantum mechanical effects. White dwarfs are the fate-awaiting stars like our Sun. When the Sun exhausts its hydrogen fuel, it will expand into a red giant, fusing helium in its core and hydrogen in a shell around it. Eventually, it will blow off its outer layers, creating a planetary nebula, and the core will remain behind as a white dwarf. A white dwarf is supported by electron degeneracy pressure. This is a quantum mechanical effect arising from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. When you compress matter to extreme densities, electrons are forced into higher and higher energy states. This creates a pressure that's independent of temperature. A typical white dwarf contains about 60% of the Sun's mass compressed into a sphere, roughly the size of Earth. The density is approximately 1 million times that of water. A sugar cube of white dwarf material would weigh about 1 ton. The surface gravity is roughly 100,000 times Earth's gravity. Despite their incredible density, white dwarfs are not particularly hot when they form. They're born with surface temperatures around 100,000 Kelvin, but they have no internal heat source. They cannot fuse elements because the temperatures and pressures aren't high enough to overcome electron degeneracy, so they simply cool down over billions of years, radiating away their thermal energy into space. The coolest white dwarfs we've observed have surface temperatures around 3000 Kelvin, glowing faintly in the infrared. Eventually, after tens or hundreds of billions of years, they will cool to the point where they no longer emit significant radiation. They'll become black dwarfs, cold spheres of degenerate matter drifting through the darkness. The universe isn't old enough for any black dwarfs to exist yet, but give it time. Some white dwarfs don't cool peacefully. If a white dwarf exists in a binary system with a companion star, it can pull matter from that companion. Hydrogen accumulates on the white dwarf's surface, compressed by the intense gravity. Eventually the pressure and temperature trigger runaway fusion. The entire accumulated layer detonates in a nova explosion, blowing the surface material back into space. This isn't a supernova. The white dwarf survives, and after some time the process can repeat. Some stars undergo nova eruptions multiple times, separated by decades or centuries. It's a cycle of accumulation and explosion that can continue for millions of years. But if the white dwarf gains enough mass, if it approaches the Chandrasekhar limit, something different happens. At 1.4 solar masses, electron degeneracy pressure can no longer support the star. The entire white dwarf, not just a surface layer, undergoes runaway fusion. Carbon and oxygen fuse in an uncontrolled chain reaction. The star detonates. This is a Type Ia supernova, and it completely destroys the white dwarf. Type Ia supernovae are remarkably consistent in their peak brightness because they always occur at the same mass limit. This makes them useful as standard candles for measuring cosmic distances. By comparing their apparent brightness to their known absolute brightness, we can calculate how far away they are. It was observations of distant Type Ia supernovae that led to the discovery of dark energy and the accelerating expansion of the universe. Between white dwarfs and neutron stars, there's a theoretical object we've never definitively observed. Quark stars, if they exist, would be supported by quark degeneracy pressure. Instead of neutrons, the matter would be broken down into free quarks. The density would be intermediate between neutron stars and black holes, and the surface would be unimaginably strange. A liquid of quarks with properties unlike any matter we can create in laboratories. Some researchers believe certain observed neutron stars might actually be quark stars, but we can't tell from external observations alone. The differences in mass and radius are too subtle. We would need to observe a starquake or measure extremely precise gravitational wave signals to distinguish them. There are stars that exist in multiple extreme states simultaneously. Thorne-Zhitkov objects are theoretical hybrid stars with a neutron star core surrounded by a massive stellar envelope. Imagine a neutron star embedded inside a red supergiant, the neutron star orbiting within the larger star's atmosphere. It sounds impossible, but the physics allows it. We think we've found a few candidates, but confirmation is difficult. Then there are stars that shouldn't exist at all, but somehow do. Population 3 stars are purely theoretical, the first generation of stars that formed after the Big Bang. They would contain no elements heavier than hydrogen and helium because those elements didn't exist yet. Models predict they would be massive, hundreds of solar masses, burning bright and fast before exploding as pair instability supernovae. We've never seen a population 3 star directly. They existed too long ago. But we're looking, using the James Webb Space Telescope to peer back to the earliest epochs of star formation. If we can find one, it would tell us about the conditions in the infant universe, about how the first elements were created, about how galaxies began to form. There are stars that pulse with mathematical precision. Cepheid variables expand and contract in regular cycles, their brightness varying as they do. The period of pulsation is directly related to their absolute luminosity. Brighter Cepheids pulse more slowly. This relationship, discovered by Henrietta Swan Leavitt in the early 20th century, gave us another standard candle for measuring cosmic distances. RR Lyrae variables are similar but less luminous, useful for measuring distances within our galaxy. Delta Scuti variables, Beta Cepheid variables, each class pulses for different physical reasons and provides different information. The universe is full of clocks, stars that beat out rhythms we can use to map space and time. And then there are the truly bizarre cases. Przybylski's star is a chemically peculiar star that contains elements that shouldn't exist in stellar atmospheres. It shows spectral lines of plutonium, a radioactive element with a half-life of 80 million years. There's no known way for a star to maintain plutonium in its atmosphere for long periods. Some exotic nuclear process must be occurring, something we don't understand. KIC US N462852, also known as Boyajian star or Tabby star, exhibits irregular dimming patterns that don't match any known astronomical phenomenon. The brightness drops by up to 22% at irregular intervals. Comets, dust clouds and debris from planetary collisions have all been proposed as explanations. None fit perfectly. The star remains an enigma, a reminder that we don't have all the answers. Some stars move at incredible velocities. Hypervelocity stars are objects travelling fast enough to escape the Milky Way's gravitational pull. Speeds exceed 500 kilometers per second. Most are thought to be former binary companions of stars that venture too close to the supermassive black hole at the galactic centre. The black hole captured one star and flung the other outward at extreme velocity in a gravitational slingshot. S5 HVS1 is moving at 1800 kilometers per second, fast enough to cross the distance from Earth to the Moon in about 3.5 minutes. It will leave the Milky Way and drift through intergalactic space for eternity, a lonely exile travelling through the void between galaxies. Binary stars are far more common than single stars like our Sun. About half of all stars exist in binary or multiple star systems, locked in gravitational dances with companions. Some binaries are widely separated, taking thousands of years to orbit each other. Others are so close their atmospheres touch, transferring mass back and forth in complex tidal interactions. Contact binaries are systems where both stars share a common envelope. They orbit so closely that they're essentially a single peanut-shaped object. These systems can merge entirely, creating a new, more massive star, or they can remain in contact for millions of years, gradually spiraling closer due to gravitational wave radiation. V Sagittae is a binary system predicted to explode around the year 2083, give or take 16 years. A white dwarf is pulling so much matter from its companion that it will exceed the Chandrasekhar limit within decades. When it does, it will detonate in a Type Womea supernova that will briefly become one of the brightest stars in Earth's night sky. We're watching a cosmic timer count down. Eclipsing binaries provide some of our most precise measurements of stellar properties. When one star passes in front of the other from our perspective, the combined light dims. By studying these eclipses, we can determine the star's sizes, masses, and orbital parameters with extraordinary precision. Algol, the demon star, is an eclipsing binary whose variations were noted by ancient astronomers. Its name comes from the Arabic phrase Ras al-Ghul, meaning the demon's head. Some stars refuse to behave. T-Tauri stars are young, variable stars still in the process of formation. They're surrounded by protoplanetary disks and exhibit irregular outbursts and flares. Herbig A-B stars are similar but more massive. These are stars being born, accreting material from the clouds around them, fighting against their own formation process. Few Orionis stars are another class of young variables that suddenly brighten by several magnitudes and remain bright for decades or centuries before fading again. The cause is thought to be rapid accretion from the protoplanetary disk, but the trigger mechanism is unclear. We're watching the chaotic violence of stellar birth. Brown dwarfs occupy a strange territory between planets and stars. They form like stars from the gravitational collapse of gas clouds, but they never achieve the mass necessary to sustain hydrogen fusion. They're too massive to be planets, typically ranging from 13 to 80 times Jupiter's mass, but too small to be stars. In the cores of brown dwarfs, temperatures reach a few million Kelvin. This is hot enough to fuse deuterium, a heavy isotope of hydrogen, but not hot enough for sustained hydrogen fusion. They burn through their limited deuterium fuel in a few million years, then spend the rest of their existence slowly cooling and fading. The coolest brown dwarfs we've discovered have surface temperatures below 300 Kelvin, colder than the boiling point of water. Some have atmospheres containing water vapor clouds. Others show evidence of methane. These are objects that blur the line between failed stars and super-Jovian planets. The distinction becomes philosophical rather than physical. WISE 0855 07RSIM4 is a brown dwarf with a surface temperature around 250 Kelvin, about -23 Celsius. It's roughly 7 light-years from Earth, making it one of the Sun's nearest neighbours. Observations suggest it has water ice clouds in its atmosphere, a frozen star drifting through space, radiating faintly in the infrared. The coolest known brown dwarf, WISE 1828 Pl-2650, has an estimated temperature around 200 Kelvin, colder than any planet in our solar system. At these temperatures, the distinction between a very cold brown dwarf and a free-floating planet becomes meaningless. They're the same type of object, differing only in formation mechanism. Some brown dwarfs rotate incredibly fast. WISE PC JL12254 konstatintruisas platustu farvam via verstu 2-1.5 completes one rotation every 1.4 hours. The equatorial velocity approaches 60 km per second. The centrifugal force nearly tears the object apart, flattening it into an oblate shape. These rapid rotators challenge our understanding of angular momentum in star formation. There's a population of rogue planets and brown dwarfs wandering through the galaxy, untethered to any star. Estimates suggest there might be billions of these objects in the Milky Way alone, dark and nearly invisible, detectable only when they pass in front of background stars or emit faint infrared radiation. Some of these rogues were ejected from planetary systems through gravitational interactions. Others formed independently in molecular clouds and were never part of a solar system. They drift through interstellar space, slowly cooling, utterly alone. If one passed through our solar system, we might not detect it until it was already leaving. The study of stellar remnants reveals the universe's recycling program. Nothing is truly lost. When stars explode, they enrich the interstellar medium with heavy elements. These elements become part of new generations of stars and planets. Every complex atom in your body was created inside a star or during a supernova explosion. The iron in your blood was forged in the core of a massive star during the final moments before it collapsed. The calcium in your bones, the carbon in your DNA, the oxygen you breathe, all stellar products. You're not just made of star stuff, you're made of the ashes of stellar catastrophes. Supernova remnants are visible evidence of this process. The Crab Nebula is the expanding debris from a supernova observed by Chinese and Arab astronomers in 1054 CE. It's now about 11 light-years across and still expanding at roughly 1500 kilometers per second. At its center is a pulsar. the neutron star remnant, spinning 30 times per second and powering the nebula's glow through its intense magnetic field and relativistic particle wind. The Vela supernova remnant is much older and larger, roughly 100 light-years across. The supernova that created it exploded about 11,000 years ago, well before recorded human history. The remnant is now colliding with surrounding interstellar clouds, shocking and compressing the gas, potentially triggering new star formation. Death leads to birth. Cassiopeia A is the remnant of a supernova that should have been visible from Earth around 1670, but there are no reliable historical records of anyone seeing it. Either it was obscured by interstellar dust, or the explosion was intrinsically fainter than typical supernova. The remnant is now about 10 light-years across, and detailed observations reveal knots and filaments of material moving at thousands of kilometers per second. Each supernova remnant is unique, shaped by the progenitor star's structure, the surrounding core environment, and the explosion dynamics. Some are roughly spherical, others are highly asymmetric, reflecting instabilities in the explosion or interactions with pre-existing stellar wind bubbles. Inside these remnants, cosmic rays are accelerated to near-light speeds. The shock waves from supernovae are among the most efficient particle accelerators in nature. Protons and atomic nuclei are caught in the chaotic magnetic fields and repeatedly bounced back and forth across the shock front, gaining energy with each crossing. By the time they escape, some have energies millions of times higher than particles in our most powerful accelerators. These cosmic rays permeate the galaxy. Some eventually reach Earth, passing through your body at this very moment. A few carry enough energy to trigger detectable particle cascades when they strike the upper atmosphere. The most energetic cosmic ray ever detected, the Oh My God particle observed in 1991, had an energy of about 300 million trillion electron volts. It was a single proton carrying the kinetic energy of a baseball thrown at 90 kilometers per hour, concentrated in a space a trillion times smaller. We still don't know what could accelerate particles to such extreme energies. Supernova remnants can explain most cosmic rays, but not the highest energy ones. Those might come from active galactic nuclei, from gamma-ray bursts, or from processes we haven't yet imagined. Stellar nucleosynthesis, the creation of elements inside stars, follows predictable pathways. In main sequence stars, hydrogen fuses to helium through the proton-proton chain, or the CNO cycle. In more massive stars, helium fuses to carbon and oxygen. Carbon and oxygen fuse to neon, magnesium, silicon. Silicon fuses to iron. Each stage requires higher temperatures and occurs faster than the previous one. A star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, a few thousand years fusing carbon, and mere days fusing silicon to iron. The final stages are a headlong rush toward collapse, but fusion stops at iron. To create heavier elements, you need different processes. This process, or slow neutron capture process, occurs in red giant stars. Neutrons are captured by atomic nuclei at a rate slow enough that radioactive isotopes have time to beta decay before capturing another neutron. This creates elements up to about bismuth. The R process, or rapid neutron capture, requires intense neutron fluxes that don't exist in normal stellar environments. For decades, astronomers debated where the R process occurred. Supernovae were the leading candidate, but models struggled to produce the right conditions. Then, in 2017, we observed a neutron star merger. The event was detected first by gravitational wave observatories as GW17817. Two neutron stars, each about 1.4 solar masses, had been spiraling together for millions of years, losing energy to gravitational radiation. In the final seconds, they accelerated to a significant fraction of light speed before colliding and merging. The collision produced a kilonova, an explosion powered not by fusion or core collapse, but by the radioactive decay of freshly synthesized heavy elements. observations across the electromagnetic spectrum revealed signatures of gold, platinum, and other heavy elements being created in vast quantities. A single neutron star merger can produce several Earth masses worth of gold. This observation revolutionized our understanding of where heavy elements come from. Roughly half the elements heavier than iron in the universe were created in neutron star mergers. The gold in jewellery, the platinum in electronics, the rare Earth elements in modern technology, all forged in the most violent collisions the universe can produce short of black hole mergers. The merger also answered another long-standing question. The resulting object, combining nearly 3 solar masses, should have immediately collapsed into a black hole. But there was a delay. For a few seconds, a hypermassive neutron star existed, an object that should be impossible, supported temporarily by rapid rotation and exotic physics we don't fully understand. Then it collapsed, and a black hole was born. We detected this through the gravitational wave signal. The waves showed the inspiral, the merger, and then a sudden cut-off corresponding to the formation of an event horizon. From that moment on, no information could escape. The gravitational waves stopped not because the system stopped radiating, but because the radiation was trapped inside the event horizon. Gravitational waves themselves are ripples in space-time, predicted by Einstein's general relativity and detected for the first time in 2015. When massive objects accelerate, they create distortions in the fabric of space and time that propagate outward at the speed of light. These waves compress and stretch space as they pass, but the effect is incredibly small. The first detection, GW524, came from 2 black holes, 29 and 36 solar masses, merging 1.3 billion light-years away. At the peak of the merger, the system radiated more power and gravitational waves than all the stars in the observable universe combined. And yet, when the waves reached Earth, they stretched and compressed space by less than 1,000th the diameter of a proton. Detecting this required building the most precise measuring instruments ever created. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses laser interferometry to measure changes in the length of 4-kilometre-long arms. The precision is so extreme that it can detect disturbances smaller than the nucleus of an atom, across a distance of 4 kilometres. The facility has to account for seismic noise from ocean waves on distant coasts, for thermal fluctuations in the mirrors, for quantum uncertainty in the number of photons in the laser beams. Every conceivable source of noise had to be characterised and minimised. The fact that it works at all is a testament to human ingenuity. Since the first detection, dozens of gravitational wave events have been observed. Black hole mergers, neutron star mergers, and events that might be neutron star black hole mergers. Each detection teaches us about objects in extreme conditions we can never replicate on Earth. The black holes detected through gravitational waves have masses that surprised astronomers. Some are more massive than we thought a stellar collapse could produce. Others merge in environments where we didn't expect to find them. The distribution of masses and spins is revealing details about how massive stars evolve and die. Some merging black holes have spins misaligned with their orbital angular momentum. This suggests they didn't form together as a binary system, but were brought together through dynamical interactions in dense stellar environments like globular clusters or galactic nuclei. They're cosmic strangers that met by chance and became bound by gravity. The study of stellar evolution has revealed surprising connections between different types of objects. Wolf-Rayet stars are massive stars that have lost their outer hydrogen layers, exposing their helium cores. They're incredibly hot, with surface temperatures exceeding 30,000 Kelvin, and they shed mass through intense stellar winds at rates of 1 solar mass every 100,000 years. These stars are the likely progenitors of some supernovae and gamma-ray bursts. When a Wolf-Rayet star explodes, the lack of a hydrogen envelope changes the supernova's spectral characteristics. These are classified as type Ib or type Eq supernovae, depending on whether helium lines are present. Some Wolf-Rayet stars exist in binary systems with massive companions. The two stars can be so close that they share a common envelope, transferring mass back and forth. These systems are evolutionary laboratories, allowing us to study how mass transfer affects stellar development. Luminous blue variables are another class of massive unstable stars. They undergo irregular eruptions, ejecting significant amounts of mass in events that can briefly make them appear as bright as supernovae without actually exploding. Eta Carinae is the most famous example, having erupted in the 1840s in an event called the Great Eruption. During this outburst, Eta Carinae became the second brightest star in the sky, despite being 7,500 light-years away. It ejected at least 10 solar masses of material, creating the Homunculus Nebula, a bipolar structure of gas and dust still visible today. The star survived the eruption and continues to shed mass, but we don't fully understand what triggered the event or whether it will happen again. Eta Carinae is actually a binary system with an orbital period of 5.5 years. The primary star contains about 90 solar masses, while the companion is around 30 solar masses. When they approach closest approach, their stellar winds collide, creating X-ray emission and complex interactions we're still working to understand. This system is a supernova waiting to happen. Sometime in the next 100,000 years, possibly much sooner, Eta Carinae will explode. Given its mass, it might produce a gamma-ray burst, a beam of intense radiation that could affect Earth's atmosphere if aimed in our direction. We're probably safe. Probably. Gamma-ray bursts are among the most energetic events in the universe. They come in two types. Short-duration bursts, lasting less than 2 seconds, are thought to come from neutron star mergers. Long-duration bursts, lasting more than 2 seconds, are associated with the collapse of very massive stars, particularly Wolf-Rayet stars, in a type of supernova called a hypernova or collapsar. In a collapsar, event, the core of a massive star collapses to form a black hole, but the outer layers don't immediately explode outward. Instead, they fall inward, forming an accretion disk around the newly formed black hole. The black hole's rotation and magnetic fields drive powerful jets of plasma outward along the rotation axis. When these jets break through the stellar envelope and escape into space, they create a gamma-ray burst. The energy focused into these jets is almost incomprehensible. A typical long-duration gamma-ray burst releases as much energy in a few seconds as the Sun will produce in its entire 10 billion-year lifetime. And this is only the energy in the jets. The total energy of the explosion is even greater. If a gamma-ray burst occurred within a few thousand light-years of Earth, and the jet pointed at us, the gamma radiation would destroy the ozone layer, exposing the surface to lethal solar ultraviolet radiation. This could trigger a mass extinction. Some researchers have proposed that the Ordovician extinction, 440 million years ago, might have been caused by a nearby gamma-ray burst. Fortunately, gamma-ray bursts are rare, and the odds of one occurring close enough and aimed precisely at Earth are very low. But the universe is large and old. Over billions of years, the probability approaches certainty. It's happened before. It will happen again. The brightest gamma-ray burst ever detected, GRB 2022-1009A, occurred in October 2022. It was so bright that it saturated detectors and affected Earth's ionosphere from 2 billion light-years away. The energy output was extraordinary even by gamma-ray burst standards. Events like this remind us that the universe operates on scales that dwarf anything in human experience. Stellar physics is intimately connected to nuclear physics. The same forces that govern atomic nuclei determine what happens in stellar cores. The strong nuclear force binds protons and neutrons together in nuclei. The weak force governs beta decay and the reactions that power the Sun. Electromagnetism keeps electrons in orbit and creates the pressure that supports white dwarfs. Gravity is the weakest of the 4 fundamental forces, but it acts over infinite range and only attracts. Over large scales, gravity dominates. It's gravity that assembles gas clouds into stars, gravity that compresses cores until fusion ignites, gravity that ultimately causes stellar collapse. The interplay between these forces determines the universe's structure. If the strong force was slightly weaker, deuterium wouldn't form, and stars couldn't fuse hydrogen. If it were slightly stronger, protons would bind into diprotons and stars would burn through their fuel almost instantly. The universe would be very different. If the weak force was stronger, supernovae might not work. The neutrinos produced during core collapse would be trapped, unable to carry away energy and unable to drive the explosion. Stellar evolution would stall. Heavy elements might never form. The constants of nature appear finely tuned to allow complex structures like stars, planets, and life. This observation has led to much speculation. Some invoke the anthropic principle. We observe these values because only universes with these values can produce observers. Others propose multiverse theories where different regions have different constants, and we simply exist in a region compatible with our existence. These are deep questions that touch on physics, philosophy, and perhaps theology. Stars in their life and death embody these fundamental principles. They're laboratories where we can observe the laws of nature operating at extremes. The life cycle of stars is deterministic. Give us a star's initial mass, and we can predict its entire future with reasonable accuracy. Low-mass stars become red dwarfs, burning slowly for trillions of years. Medium-mass stars like our Sun become red giants, then white. Dwarfs, massive stars, explode as supernovae, leaving behind neutron stars or black holes. But within this determinism, there's extraordinary variety. Stars of the same mass can evolve differently depending on their composition, rotation rate, magnetic field strength, and whether they have companions. Binary interactions can completely alter evolutionary pathways. Red dwarf stars, those with masses below about 40% of the Sun, are the most common stars in the galaxy. They're also the longest lived. A red dwarf with 10% of the Sun's mass will burn for 10 trillion years, roughly 700 times the current age of the universe. None of the red dwarfs that formed in the early universe have died yet. They're still on the main sequence, steadily fusing hydrogen. These stars are completely convective. The entire interior churns and mixes, bringing fresh hydrogen from the outer layers down to the core. This means red dwarfs can eventually fuse nearly all their hydrogen, not just the central reservoir. When they finally exhaust their fuel, they won't become red giants. They'll transition directly to blue dwarfs, then white dwarfs, over timescales longer than the universe has existed. Proxima Centauri, the closest star to our solar system, is a red dwarf located 4.24 light-years away. It's a small star, about 12% of the Sun's mass and 1.5% of its luminosity. Despite being our nearest stellar neighbour, it's invisible to the naked eye. You need a telescope to see it. Proxima Centauri is a flare star. It experiences sudden, dramatic increases in brightness, caused by magnetic reconnection events on its surface. These flares can increase the star's luminosity by several times for minutes to hours. The magnetic fields on red dwarfs are often much stronger than on stars like the Sun, and the flares correspondingly more violent. This creates challenges for planets orbiting red dwarfs. Proxima Centauri has at least 2 planets, including Proxima Centauri b, which orbits within the star's habitable zone. But the frequent powerful flares bathe the planet in radiation that could strip away atmospheres and sterilize surfaces. Whether life could survive in such an environment is an open question. Red dwarfs might be the universe's best hope for long-term habitability. They'll outlive all other types of stars. In the far future, when massive stars have long since died, and even sun-like stars have become white dwarfs, red dwarfs will still be shining. Any civilizations that survive to the deep future might find homes around these patient, persistent stars. Barnard's star is another nearby red dwarf, about 6 light-years away. It has the largest proper motion of any star, moving across the sky at 10.3 arc seconds per year. This high motion is mostly due to its proximity and its velocity relative to the Sun. In about 10,000 years, Barnard's star will be the closest star to our solar system, approaching to within about 3.8 light-years before receding again. For decades, astronomers thought Barnard's star had planets. Observations in the 1960s and 70s suggested perturbations in its motion, consistent with one or more large planets. But these detections were ultimately attributed to systematic errors in the measurements. It wasn't until 2018 that a confirmed planet, Barnard's star B, was discovered through radial velocity measurements. This planet is a super-Earth with a minimum mass about 3 times Earth's, orbiting every 233 days. The search for planets around other stars has revolutionized our understanding of stellar systems. We now know that planets are common, that most stars have them, and that the architectures of planetary systems are far more diverse than we imagined. Hot Jupiters, gas giants orbiting extremely close to their stars, were among the first exoplanets discovered. These shouldn't exist according to planet formation theories of the time. Gas giants should form far from their stars where it's cold enough for ices to condense. Yet here were Jupiter-sized planets, with orbital periods of just a few days, surface temperatures exceeding 1000 Kelvin, and year lengths shorter than an Earth week. We now understand that planets can migrate after formation. Interactions with the protoplanetary disk or with other planets can cause orbits to change dramatically. Hot Jupiters likely formed farther out and spiraled inward. Some might have migrated so close that their atmospheres are being stripped away by stellar radiation. WASP 12b is a hot Jupiter that's being destroyed by its star. The planet orbits so closely that tidal forces have stretched it into an egg shape. The star's intense radiation heats the atmosphere to over 2500 Kelvin, causing it to expand and overflow the planet's gravitational pull. Material is being stripped away and accreted by the star. In about 10 million years, the planet will be completely consumed. Other exotic exoplanets include super-Earths, planets more massive than Earth, but less massive than Neptune, with no analogue in our solar system. Mini-Neptunes are ice giants smaller than Neptune and Uranus. Some planets orbit binary stars, experiencing complex gravitational dynamics and bizarre seasonal variations. Others are rogue planets, ejected from their systems and wandering through interstellar space. Kepler 16b is a planet that orbits 2 stars, a real-world Tatooine. The planet experiences eclipses from both stars, and the gravitational perturbations from the binary make its orbit precess significantly over time. Standing on the surface, you would see 2 suns in the sky, one larger and brighter, the other smaller and dimmer, both rising and setting at different times. The diversity of exoplanets suggests that planet formation is a robust process that occurs under a wide range of conditions, but it also shows that our solar system, with its neat arrangement of rocky planets near the Sun and gas giants farther out, is just one configuration among many. There's no typical planetary system. Each is a unique outcome of chaotic processes during the protoplanetary disk phase. Stars themselves show enormous diversity in their surface compositions. Most stars are primarily hydrogen and helium, with small amounts of heavier elements, but the exact proportions vary. Older stars formed when the galaxy was young have lower metallicity. They contain fewer heavy elements, because those elements hadn't been created yet by previous generations of stars. Population 1 stars are metal-rich. Young stars found in the galactic disk and spiral arms. Population 2 stars are metal-poor. Older stars found in the galactic halo and globular clusters. The theoretical population 3 stars would have 0 metals, composed only of primordial hydrogen and helium. Metallicity affects stellar evolution. Metal-rich stars have more opaque atmospheres, which affects heat transport and surface temperature. They also have different fusion rates. Metallicity influences whether a star will become a red supergiant or a blue supergiant before exploding, which in turn affects the type of supernova it produces. Some stars show chemical peculiarities that don't fit standard models. Chemically peculiar stars have abnormal abundances of certain elements in their atmospheres. AP stars show enhanced levels of elements like strontium, chromium, and europium. The cause is thought to be radiative diffusion, where radiation pressure pushes certain elements toward the surface, while gravity pulls others down, creating stratified layers. Barium stars are giants with abnormally high barium and other S-process elements. They're typically found in binary systems where a companion white dwarf, now dead and cooling, was once an AGB star that produced S-process elements and transferred them to the current giant through stellar wind or Roche-Lobe overflow. Carbon stars have more carbon than oxygen in their atmospheres, reversing the usual ratio. This occurs in late-stage red giants where dredge-up events bring carbon produced in the core to the surface. These stars appear deep red and are surrounded by sooty carbon dust. The Sun itself is a variable star, though the variations are small. The solar cycle, approximately 11 years long, sees changes in the number of sunspots, solar flares, and coronal mass ejections. During solar maximum, the Sun is slightly brighter and more active. During solar minimum, it's quieter. These variations affect Earth. Solar flares and coronal mass ejections can disrupt satellite communications, damage power grids, and create auroras. The largest recorded solar storm, the Carrington event of 1859, caused telegraph systems to fail and produced auroras visible as far south as the Caribbean. If a similar storm occurred today, the damage to modern infrastructure could be catastrophic. The Sun's magnetic field flips every 11 years. The north and south magnetic poles swap positions. This flip is associated with the solar cycle and the movement of magnetic flux through the solar interior and atmosphere. We don't fully understand the dynamo mechanism that generates the Sun's magnetic field, though we know it involves the interaction of rotation and convection. Sunspots are temporary dark regions on the Sun's surface, where intense magnetic fields inhibit convection, reducing the surface temperature. A typical sunspot has a temperature around 4,000 Kelvin, compared to the surrounding photosphere at 5,700 Kelvin. They appear dark only by contrast. If you could see a sunspot in isolation, it would shine brighter than the full moon. The number of sunspots varies with the solar cycle. During solar maximum, dozens of sunspot groups can be visible simultaneously. During solar minimum, the Sun can go for weeks without any visible spots. Long-term records of sunspot observations dating back to the early 17th century show that the cycle isn't perfectly regular. There have been periods, like the Maunder minimum from 1645 to 1715, when sunspots nearly disappeared for decades. The Maunder minimum coincided with the coldest part of the Little Ice Age in Europe. Whether the reduced solar activity caused the cooling, or merely coincided with it, remains debated. The Sun's total energy output probably didn't change by more than a fraction of a percent, but small changes in solar UV output could affect Earth's upper atmosphere and climate patterns in complex ways. Studying the Sun teaches us about other stars. We can observe the solar surface, chromosphere, and corona in exquisite detail. We can measure magnetic fields, track flows in the photosphere, and watch prominences erupt. This level of detail is impossible for other stars, which remain point sources even in our largest telescopes. But the Sun is just one star, and it's not necessarily typical. It's slightly more massive and luminous than average. Its metallicity is higher than many nearby stars. Its position in the galaxy, in a relatively sparse region of the Orion Arm, might be unusual. We have to be careful about generalizing from the Sun to other stars. Stellar astronomy has progressed enormously in recent decades. We can now measure the oscillations of stars, detecting sound waves travelling through their interiors. This field, astroseismology, works like seismology on Earth. By analysing the frequencies of oscillations, we can determine a star's internal structure, rotation rate, and even the size of its core. Kepler Space Telescope observations revealed that many stars oscillate in multiple modes simultaneously. The pattern of frequencies is unique to each star, like a fingerprint. By comparing observed frequencies to models, we can constrain a star's mass, age, and composition far more precisely than through traditional methods. Some stars pulsate regularly due to instabilities in their structure. Classical Cepheid variables undergo radial pulsations, expanding and contracting over periods of days to months. The pulsation occurs because of a zone in the stellar envelope where helium is partially ionized. This zone acts as a valve, trapping heat during compression and releasing it during expansion, driving oscillations. The period luminosity relationship for Cepheids has been refined over a century of observations. It's now one of the most important tools for measuring cosmic distances. By observing Cepheids in nearby galaxies and measuring their periods, we can calculate their absolute luminosities, compare to their apparent brightnesses, and determine how far away they are. Henrietta Swan Leavitt discovered this relationship while studying Cepheids in the Magellanic Clouds. She never received the recognition she deserved during her lifetime, but her work laid the foundation for our understanding of the universe's scale. Without Leavitt's law, we might still think the Milky Way was the entire universe. RR Lyrae stars are similar to Cepheids, but less luminous and with shorter periods. They're old population 2 stars found in globular clusters in the galactic halo. Because they all have similar absolute magnitudes, they serve as standard candles for measuring distances within the Milky Way. Globular clusters are ancient stellar cities, spherical collections of hundreds of thousands to millions of stars, all formed at roughly the same time from the same gas cloud. They orbit in the galactic halo, following elliptical paths that take them far above and below the galactic disk. The stars and globular clusters are among the oldest in the universe, typically 10 to 13 billion years old. They're metal poor, reflecting the composition of the early galaxy before many generations of supernovae had enriched the interstellar medium. Studying globular clusters gives us a window into the early universe, showing us what the first large-scale stellar populations looked like. Omega Centauri is the largest globular cluster in the Milky Way, containing about 10 million stars. It's so massive and unusual that some astronomers think it might be the stripped core of a dwarf galaxy that merged with the Milky Way long ago. Its stars show a range of ages and metallicities, unusual for a globular cluster, supporting the dwarf galaxy hypothesis. Inside globular clusters, stars are packed densely enough that gravitational interactions are common. Stars can exchange companions in binary systems. Some stars collide and merge, forming blue stragglers, stars that appear younger and more massive than they should be. These collision products briefly revive, fusing hydrogen that was mixed into their cores during the merger. Globular clusters also host large populations of exotic objects. Millisecond pulsars, neutron stars spun up by mass transfer from companions, are common. X-ray binaries, where a neutron star or black hole accretes matter from a companion star, create bright X-ray sources. The dense environment accelerates stellar evolution through interactions. Some globular clusters contain intermediate mass black holes, objects with masses between stellar mass black holes and supermassive black holes. These are rare and difficult to detect, but they appear to exist at the centres of some massive globular clusters. They might form through repeated mergers of smaller black holes or through the collapse of very massive stars in the early universe. The study of stellar populations extends beyond individual stars to understanding how stars collectively evolve in different environments. Star-forming regions like the Orion Nebula show us stars being born. Open clusters like the Pleiades show us young stars still close to their birthplace. Globular clusters show us ancient populations in retirement. Each environment tells a story. In star-forming regions, we see massive stars forming alongside smaller ones, the initial mass function playing out in real time. We see protoplanetary disks, planetary systems in formation. We see the feedback from massive stars, their radiation and stellar winds shaping the gas clouds around them. In young open clusters, massive stars have already begun to die, exploding as supernovae and enriching the remaining gas. The cluster starts to disperse as stellar orbits become unbound through gravitational interactions. Most open clusters dissolve within a few 100 million years, their stars spreading throughout the galaxy. In globular clusters, all the massive stars died billions of years ago. What remains are low-mass stars, white dwarfs, neutron stars, and perhaps a few black holes. The cluster evolves through two-body relaxation, where gravitational interactions gradually redistribute energy among stars. Some stars gain energy and escape. Others lose energy and sink toward the core, increasing the central density. This process can lead to core collapse, where the center of the globular cluster becomes extremely dense. Eventually, three-body interactions become important. When three stars approach closely, one is typically ejected at high velocity while the other two form a tighter binary. These dynamical processes have been sculpting globular clusters for billions of years. The galaxy itself is a stellar ecosystem, a vast network of interconnected processes where stars are born, live and die, feeding material back into the cosmic cycle. The interstellar medium, the gas and dust between stars, is both the womb and the grave of stellar populations. Molecular clouds are the birthplaces of stars. These are dense, cold regions of space, shielded from starlight, where temperatures drop to just 10 or 20 Kelvin above absolute zero. In these frigid conditions, atoms combine to form molecules. Hydrogen molecules, carbon monoxide, water, ammonia, even complex organic compounds exist in these clouds. The densest parts of molecular clouds can collapse under their own gravity. When a region becomes gravitationally unstable, it fragments and begins to contract. As it contracts, it heats up. Conservation of angular momentum causes it to spin faster and flatten into a disk. At the center, a protostar forms. A protostar is not yet a star. It's a growing accumulation of matter still gaining mass from the surrounding cloud. The center is hot, but not hot enough for fusion. Energy comes from gravitational contraction, from the conversion of potential energy to heat as matter falls inward. This phase can last for hundreds of thousands to millions of years, depending on the final mass. Eventually, the core temperature reaches about 10 million Kelvin. Hydrogen fusion ignites. The protostar becomes a star, settling onto the main sequence where it will spend most of its life. The remaining disk material either forms planets, gets blown away by stellar winds, or falls into the star. Not all the material in a molecular cloud ends up in stars. Much of it is dispersed by the radiation and winds from newly formed massive stars. These stars, hot and bright, ionize the surrounding gas, creating He regions, glowing clouds of ionized hydrogen. The Orion Nebula is an He region, one of the brightest and most studied in the night sky. It's about 1,300 light-years away, close enough that we can resolve individual stars and protoplanetary disks. At its heart are four massive stars, the trapezium, whose radiation illuminates the nebula and sculpts its structure. Behind the visible nebula lies the Orion Molecular Cloud Complex, a vast structure containing enough gas to form thousands of stars. Star formation is ongoing. Infrared observations reveal protostars still hidden within dusty cocoons, visible only in wavelengths that penetrate the dust. Star formation is a feedback process. Massive stars, through their radiation, winds and eventual supernovae, inject energy into the interstellar medium. This can both trigger and suppress further star formation. Shocks from supernovae can compress nearby gas clouds, initiating new collapse. But the same shocks can also disperse clouds, preventing them from forming stars. Over billions of years, this process enriches the galaxy with heavy elements. Each generation of stars contains more metals than the last. The first stars, population 3, had none. The Sun, a relatively young population 1 star, has about 2% of its mass in elements heavier than helium. Future generations will be even more metal-rich. This chemical evolution affects planet formation. Planets require heavy elements. The very first stars probably had no planets, or at most gas giants formed from the primordial hydrogen and helium. Rocky planets like Earth require carbon, oxygen, silicon, iron, elements that only exist because previous stars created them. In this sense, we are profoundly connected to stellar evolution. The Earth itself is a product of stellar nucleosynthesis. The ground beneath your feet, the air you breathe, the water in the oceans, all assembled from atoms forged in stars and scattered by supernovae. There's a certain poetry in this. We spend our lives on the surface of a planet made of stardust, looking up at the stars that created us, trying to understand the processes that led to our existence. Astronomy is perhaps the most introspective science. In studying the universe, we study our origins. The timescales of stellar processes dwarf human experience. We live for decades. Stars live for millions to trillions of years. Even the short-lived massive stars burning for just a few million years outlast human civilizations. The stars we see in the night sky have been there, essentially unchanged, throughout all of recorded history. Betelgeuse, the red supergiant, marking Orion's shoulder, has been bright and recognizable for as long as humans have looked at the sky. Ancient civilizations saw the same star. It appeared in their myths, their navigation, their calendars. And yet Betelgeuse is dying. It could explode as a supernova any time within the next 100,000 years. It might have already exploded and the light simply hasn't reached us yet. When Betelgeuse does explode, it will briefly become one of the brightest objects in the sky, visible during the day, casting shadows at night. It will be a spectacular event, observable to the naked eye for weeks or months, and then it will fade, leaving behind a neutron star or black hole and an expanding remnant that will glow for thousands of years. The supernova will inject energy and heavy elements into the interstellar medium around Betelgeuse. The shock wave will propagate outward at thousands of kilometers per second, eventually slowing as it sweeps up more and more material. After tens of thousands of years, it will fade and disperse, its material mixed into the general interstellar medium, indistinguishable from the rest. And someday, millions of years from now, that material might collapse to form new stars. Some of the atoms forged in Betelgeuse's core, or created in its supernova explosion, will become part of new planetary systems. Perhaps life will arise on one of those planets, built from the remains of Betelgeuse, looking up at its own night sky and wondering about the stars. This is the cosmic cycle. Stars are not eternal, but the matter they contain is recycled endlessly. The universe doesn't create or destroy matter, only transforms it, organizing and reorganizing atoms into different structures. Our sun will die peacefully. In about 5 billion years, it will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around an inert helium core. This will cause it to expand into a red giant, growing to perhaps 100 times its current radius. Mercury will be engulfed. Venus likely as well. Earth might survive at the edge of the expanded envelope, or it might be consumed. The surface temperature will drop to about 3000 Kelvin, giving the sun a reddish colour. But its luminosity will increase to thousands of times its current value. Any water remaining on Earth will boil away. The atmosphere will be stripped into space. The surface will be scorched and melted. If Earth survives, it will be a dead, airless rock orbiting a giant star. The sun will spend about 1 billion years as a red giant. Eventually the helium core will become hot and dense enough for helium fusion to begin. This happens suddenly, in what's called the helium flash. For a few hours the core releases enormous energy, but the energy is absorbed by the surrounding layers. The star doesn't brighten noticeably from outside. After the helium flash, the sun will settle into a stable phase, fusing helium in its core and hydrogen in a shell. This phase lasts about 100 million years. When the helium is exhausted, the sun will expand again, becoming an asymptotic giant branch star, pulsating and unstable. During this phase, the Sun will lose mass through intense stellar winds. The outer layers will be blown away, enriching the surrounding space with carbon, nitrogen, and oxygen. Eventually, so much mass is lost that the envelope detaches entirely, drifting away as a planetary nebula. What remains is the core, now a white dwarf, about half the Sun's original mass compressed into an object the size of Earth. No fusion occurs. The white dwarf simply cools, radiating away its stored thermal energy over billions of years, gradually fading from white-hot to red to eventually black. This is the fate of the Sun, a quiet end after 10 billion years of steady burning. It will not explode. It will not become a neutron star or black hole. It will fade into darkness, a cooling ember in an aging galaxy. By the time the Sun dies, the Milky Way will have changed dramatically. Our galaxy is currently on a collision course with the Andromeda Galaxy. In about 4 billion years, the two will begin to merge. This sounds catastrophic, but galactic collisions are gentle on stellar scales. Stars are so far apart that actual collisions between them are extremely rare. When galaxies merge, they pass through each other like ghosts. But the gravitational interactions reshape both galaxies. Spiral arms are disrupted. Gas clouds collide, triggering bursts of star formation. Some stars are flung out into intergalactic space. Over the course of 1 billion years or more, the two galaxies will merge completely, forming a larger elliptical galaxy that astronomers have already nicknamed Milkomeda. The Sun, if it still exists, will find itself in a very different galactic environment. The night sky, if anyone were around to see it, would be unrecognizable. The merger will likely bring the Sun close to the galactic centre. It might also perturb the orbits of objects in the Oort cloud, sending comets raining into the inner solar system. But by this time, the Sun will already be entering its red giant phase. The inner solar system will be uninhabitable regardless. Life on Earth, if it survives that long, will have fled or evolved beyond recognition. 1 billion years is a vast span. Life has existed on Earth for about 3.8 billion years. In another billion years, the Sun's increasing luminosity will make Earth too hot for liquid water. The oceans will evaporate. The greenhouse effect will accelerate. Earth will become like Venus, a hothouse world with surface temperatures hot enough to melt lead. Any life that survives will need to adapt to these conditions or find new homes. Perhaps life will spread to the outer solar system, to the moons of Jupiter and Saturn, which will become more hospitable as the Sun brightens. Or perhaps intelligence will develop the ability to leave the solar system, entirely seeking refuge around younger, more stable stars. These are questions for the far future, so distant that they seem almost mythological. But the stars will still be there, burning and dying, forming and dispersing, following the laws of physics with perfect indifference to the presence or absence of observers. In the very far future, trillions of years from now, star formation will cease. Molecular clouds will be exhausted. The gas and dust that fuel new stars will be locked up in white dwarfs, neutron stars, black holes, and planets. The universe will enter the degenerate era, a time when the only stars left are the longest-lived red dwarfs, slowly fading as they consume the last of their fuel. Eventually, even these will die. The universe will be dark except for the occasional flash of a white dwarf, accreting matter from a companion, or the glow of matter falling into black holes. This is the black hole era, when black holes are the dominant massive objects. Black holes themselves are not eternal. Stephen Hawking showed that quantum effects near the event horizon cause black holes to radiate energy, a process called Hawking radiation. The rate is inversely proportional to the black hole's mass. Stellar mass black holes evaporate incredibly slowly, taking 10 to the power of 67 years or more. Supermassive black holes take even longer. But given enough time, all black holes will evaporate. The universe will be left with only fundamental particles, photons, neutrinos, electrons, positrons, scattered across vast distances, with temperatures asymptotically approaching absolute zero. This is the heat death, the final state of maximum entropy. At this point, the universe will be in thermal equilibrium. No gradients exist, no energy flows, no structures form. Time, in any meaningful sense, stops. The universe doesn't end, but nothing happens anymore. It simply exists, cold and dark and empty, forever. This is the ultimate fate predicted by our current understanding of cosmology and thermodynamics. It's a bleak picture, but it's also so far in the future that it's almost meaningless. The timescales involved, 10 to the power of 100 years and beyond, are incomprehensibly vast. For comparison, the current age of the universe is only 10 to the power of 10 years, about 13.8 billion years. Before we reach the heat death, countless stellar generations will rise and fall, galaxies will merge and disperse, black holes will grow and evaporate, the universe will continue to evolve in ways we can barely imagine. And throughout it all, the basic processes we observe in stars today, fusion, collapse, radiation, will continue to operate. Stars are the universe's fundamental units of light and heat. They transform mass into energy through nuclear fusion, opposing gravity's relentless pull. This is a temporary victory. Gravity always wins in the end. But the struggle creates complexity, structure, beauty. Looking up at the night sky, you're seeing light from hundreds and thousands of ongoing nuclear reactions, each star a self-contained furnace maintaining a delicate balance. Some of these stars are younger than Earth. Others are nearly as old as the universe itself. Some are larger than our entire solar system. Others are smaller than our planet. The photons entering your eye left those stars years, decades, centuries, or millennia ago. The light from Betelgeuse left around the time William Shakespeare was writing his plays. The light from the Andromeda Galaxy began its journey when early humans were still competing with Neanderthals. The light from distant galaxies, visible only in our most powerful telescopes, has travelled for most of the age of the universe. In observing the stars, we observe the past. The universe's finite speed of light makes astronomy a time machine. We cannot see the stars as they are now. We can only see them as they were when their light began its journey. This means every observation is historical. We're studying stellar archaeology, reading the light to understand what happened long ago and far away. And yet, the stars continue. They burn, they evolve, they die, and are reborn. The processes we observe operated the same way billions of years ago and will continue billions of years into the future. The laws of physics don't change. Gravity, electromagnetism, the strong and weak nuclear forces, these are constants. In a universe of change, the laws themselves are eternal. Stars are temporary expressions of permanent principles. They emerge from chaos through gravity, shine through fusion, and return to chaos through explosive death. But the principles that govern them remain. This is perhaps the most profound realization of astronomy. We live in a universe that can be understood. The same physics that operates in our laboratories operates in the cores of stars, in the event horizons of black holes, in the hearts of galaxies. The universe is comprehensible. Not easy to comprehend, certainly. The mathematics is complex, the scales are vast, the concepts challenge intuition. But the universe follows rules. It's not arbitrary. It's not random, not in the deepest sense. There is order underlying the apparent chaos. Stars embody this order. They form in predictable ways from gas clouds. They evolve along tracks determined by their mass. They die according to well-understood processes. We can write equations that describe their behaviour, and those equations work. The predictions match observations. This doesn't diminish the wonder. If anything, understanding enhances it. Knowing that Betelgeuse is a red supergiant 900 times the diameter of the Sun, knowing it's fusing helium and carbon in nested shells around an inert iron core, knowing it will soon explode in a supernova visible across thousands of light years. All of this makes the sight of that red point of light in Orion more meaningful, not less. Every star is a story, a narrative of formation, evolution, and eventual death. Some stories are short, a few million years of brilliant burning followed by catastrophic explosion. Others are long, tens of trillions of years of patient hydrogen fusion in the dim light of a red dwarf. Each is unique in detail but follows the same basic plot. The universe is full of these stories, billions upon billions of them playing out simultaneously. Stars being born in molecular clouds, stars living on the main sequence, stars dying as white dwarfs, neutron stars, black holes. The cycle continues, matter recycling, elements accumulating, complexity increasing, and somewhere in all this, on at least one planet orbiting an ordinary yellow star in an unremarkable galaxy, matter organized itself into structures complex enough to look back at the stars and ask questions, to wonder where they came from and where they're going, to build telescopes and equations and theories. We are the universe, contemplating itself. Made of star stuff, powered by star energy, we study stars to understand our origins and our place in the cosmos. It's a fundamentally human endeavour, this search for meaning in the light of distant suns. The stars don't care whether we observe them. They burn according to physics, indifferent to poetry or philosophy, but we care. We find meaning in the patterns, beauty in the equations, wonder in the scale. We tell stories about the stars because that's what humans do. We create narratives, we seek understanding, we make meaning. And so we continue to study them, building larger telescopes, developing better theories, making more precise measurements. Each generation of astronomers pushes a little further, sees a little deeper, understands a little more. The work is never finished. There are always new questions, new mysteries, new frontiers, but perhaps that's appropriate. The universe is vast enough that we may never fully understand it. There may always be questions beyond our reach, phenomena too distant or too subtle to observe, physics operating at scales we cannot access. The universe may be fundamentally inexhaustible. If so, then the search itself becomes the point. Not the final answer, which may not exist or may be impossible to reach, but the process of discovery. The journey through increasingly sophisticated understanding, each answer revealing new questions, each solution opening new mysteries. Stars will continue to shine long after we're gone. The universe will continue its slow evolution toward maximum entropy. None of this requires human observation or comprehension. But for now, in this brief moment of cosmic history, matter has organized itself into forms capable of understanding, and we look up at the stars and see not just points of light, but nuclear furnaces, evolutionary pathways, recycling systems for the periodic table. We see our past in the stars, the creation of the elements that make up our bodies. We see our future, the death of our sun, and the transformation of our solar system. We see the present, the ongoing processes of formation and destruction that characterize the universe. And in seeing all this, in understanding even a fraction of the complexity and beauty of stellar astrophysics, we participate in something larger than ourselves. We connect to the cosmos in the deepest possible way through comprehension. We are star stuff that has learned about stars. And in that learning we find meaning. The night sky is a gift. Every clear evening is an opportunity to see billions of years of cosmic history, to witness the light from countless ongoing fusion reactions, to contemplate our place in an incomprehensibly vast universe. It costs nothing to look up. But the rewards, in wonder and understanding and perspective, are infinite. So look up tonight, find Orion if the season is right, locate Betelgeuse, that red jewel marking the hunter's shoulder. Remember that you're seeing a supergiant star 428 times the radius of our sun, burning through its final fuels, approaching the end of its 9 million year life. Remember that the light entering your eye began its journey around the time Columbus sailed to the Americas. Find the Pleiades, that little cluster that looks like a tiny dipper. Remember that you're seeing young stars, only 100 million years old, still surrounded by the gas from which they formed. Remember that in a few 100 million years this cluster will disperse, its stars scattered across the galaxy. Find whatever stars are visible from your location. Learn their names, learn their stories. Each is a world unto itself, a complex physical system operating on scales that dwarf human experience. Each follows the same fundamental laws that govern everything from atoms to galaxies. And as you look, remember that you are made of the same material as the stars. The atoms in your body were forged in stellar cores and supernova explosions. You are literally physically a part of the cosmic cycle. You're the universe experiencing itself, looking back at its own light, seeking to understand its own nature. This is the legacy of stellar astronomy. Not just facts and figures, not just equations and observations, but a profound connection to the cosmos. A recognition that we are not separate from the universe, but integral to it. We are star stuff, seeking to understand the stars, and in that seeking we fulfill perhaps the universe's deepest potential. The possibility of self-awareness, of matter understanding its own existence. The stars will continue to shine, and as long as there are minds to observe them, to wonder about them, to seek to understand them, their light will carry meaning. Not meaning inherent in the physics, but meaning we create through observation and comprehension. Meaning that emerges when consciousness encounters cosmos. This is what stars give us. Light certainly, heat, obviously, heavy elements, undeniably, but also meaning, wonder, perspective. They remind us that we are small but not insignificant, brief but not meaningless, temporary but connected to something eternal. The stars are a reminder to look beyond ourselves, beyond our immediate concerns, beyond the earth and the moment, to think in cosmic terms, to appreciate the vast scales of space and time, to recognize our place in the grand scheme of things. And in that recognition, perhaps we find peace. Not the peace of answering all questions, but the peace of accepting our place in an incomprehensible vastness. The peace of knowing that we are part of something much larger than ourselves. The peace of wonder.